So I've been asked today to talk about selectivity. So I've been doing GC for over 20 years, and I've been doing GC times GC, involved with LECO since 2001, so quite a long time. I installed the first PEG 4D in the world for Professor Ali Lewis at Leeds University in the UK. He was at the time before he moved to York. So I've got a little bit of experience with GC times GC, but that's not the purpose of my talk today, because what we're going to be doing is talking about selectivity. First of all, think about selectivity. What does it really mean? It could mean choosiness. That means the quality of carefully choosing someone or something as the best or the most suitable. So therefore, if we're going into our GC analysis, we could be selecting the technique, for example. Gas chromatography could be better for an application than liquid chromatography. Also, we can think of it as discrimination. So the property of affecting some things and not others. Now, I like to think about discrimination in terms of positive discrimination. So we always think about it in gas chromatography as a negative thing, because sometimes, you lose one analyte, you get everything as some compounds, and you lose a bit of something else, which is not good. So, for example, if you're looking at a mass range, you could be getting mass discrimination, where you're losing the higher masses. But if we try and think of discrimination in positive terms, we can use it as part of our selectivity, which I'm going to go more into in a few minutes. So, selectivity, what does it mean to you? A lot of people think automatically selectivity is this, the selectivity factor. The ability of our GC column to determine chemical and/or physical differences between two different analytes, which then allows us to separate them. Some of you might suddenly think about selectivity in the detector. We have non-selective detectors and we have selective detectors. And with selective detectors, it could be the particular detector will respond only to certain chemical bonds or chemical properties, or, for example, for different atoms or elements like sulfur detectors. So we could be thinking about selectivity on the column and the detector, but selectivity actually goes throughout our whole analysis from start to finish. So if we're doing a new sample analysis, we've got to always start from the basics. First of all, we're going to think about the sample phase. Is our sample in the gas phase, the liquid phase? Is it a solid phase sample? Or is it something in between, for example, honey, which is very difficult to suck up in a syringe, but it's not a solid either. We've also got to be thinking about the chemistry of our target compounds. What's the volatilities of them? What's their polarities? What functional groups? So you've got to think about the compounds we are interested in and analyzing. Not only do the chemistry of the target compounds we want to think about, but also the matrix. So, for example, is the matrix of high molecular weight than our target compounds? And that is where we can then start to use positive mass discrimination. Again, we'll talk more about that later. Is it a similar volatility to our analytes? So therefore, we've got to not only separate our target compounds away from each other, but also from the matrix components as well. Are they potential interference? Are they going to interfere on our GC column or in our detector? And are they the same or are they different polarities to our target compounds? We've got to think about the matrix as well as our targets. We've got to think about the concentration of our sample, but also the relative concentration between the analytes and the matrix. So therefore, if we're looking at very trace level concentration levels of our analytes, and they're in very high concentration matrix, that's going to be a lot more difficult to deal with. So we need to think about, is that going to be a problem before we start? We've got to think about the location of our samples. Where are they? How do we get them to the lab? Do we need to go and can we take a subsample to take back to our lab, or do we need to actually sample it in situ? I.e., we might even need to analyze it where it is. So the types of samples that I analyze can be from meteorites through to disease diagnosis, which is my PhD, food analysis, environmental analysis, etc. So all of them have their own difficulties. But thinking about these individual steps, first of all, before we even go into the lab, is really important. And then we can think about these things in terms of selectivity. So how do we use selectivity? More and more, we're being asked to analyze more complex samples. More and more, we're being asked to look at target compounds which are at very, very low concentration levels. So more and more, we're having to come up with more elaborate methods, better methods to actually go and analyze those samples. And again, if we've got to think about using selectivity through every single step in the process. So there's many steps, not just the instrument in front of you, but you've got to think about collection of those samples, transportation, preservation, sample preparation, before you even get to your instrument in the lab. And of course, on the other end, we've got to think about our data analysis and our reporting and how we're going to use the information that we're gathering on our instrument. So we can then start to think about using selectivity in each of those steps. So yesterday and this morning, we've been hearing about how powerful GC times GC is. We already know with time-of-flight mass specs, we can look at our full range mass spectra, and we can do things like deconvolution, etc. But what about all the other steps in between? How can we think about improving those? How can we end up with the most powerful method we can get by using selectivity to separate our analytes and our matrix in all of those steps? Got to also think about simplifying our process. If you want the ultimate sensitivity in the worst samples, then we might need to do it in every single step. However, if you don't need quite as low a sensitivity, then we could just think about using selectivity in the areas which are going to give us the biggest gains, like GC times GC, like mass spectrometers. We've got to think about, though, and understand the sample first. Yeah? Understand the question. So I was at a board meeting for the CAMS a few weeks ago, and one of the questions that came up from industry was, how do we teach new analytical chemists about asking the right questions about their samples first? Because that seems to be something that's been lost. They will just go and take a sample and try to analyze it without gathering all the information first. So that's always a starting place, thinking about your sample. So if we look at a simple system, simple GC system we've got here, we've got to think again, our steps in our process. Now, the exact steps depends on your sample and what you're trying to find out. But just a little overview of things like the sampling and sample collection we've talked about, the sample preparation, which could be manual sample preparation. It could be automated on an XYZ robot on top of your instrument, for example. Sample introduction is something I'm going to really touch on in a minute. Analyte separation, analyte detection, and then, of course, our data analysis. So all of these are big section of areas, and each of those you can break them down into smaller sections to really properly optimize your whole process, and think again about the selectivity in each of those steps. So, just spending a little bit more time on each of those sections. Sampling and sample collection. What are the aims of this? First of all, we want to collect a representative sample. So whether that's air, whether that's soil, whether that's some food, whether it's urine, lots of different matrices, but it needs to be representative. It needs to be enough for the analysis. So again, we've got to try and define how much is needed, and it needs to be in a suitable manner chosen, which is for the sample type and the sample location as well. So wherever that sample location is, which could be the other side of the world, could be in the desert, could be in a rainforest. Now, when we're bringing in selectivity in this area, we could be thinking about being selective for the volatility of the analytes that we're going to be analyzing and want to go and analyze with our instrument. So therefore, it could be you're selecting a technique which will only trap our target compounds and leave behind the matrix that we're not interested in. We could be thinking about the analyte nature, so it only traps those ones with particular functional groups, for example. It could be that we're avoiding these matrix interferences. So, for example, we are doing air analysis and we're choosing an absorbent which will trap the compounds of interest, but the water that we're not interested in is not being trapped because we're choosing a hydrophobic sorbent. Now, the techniques for sampling on site include things like the thermal desorption, where we're then optimizing the selectivity of our packing material in our TD tube. So then we draw that air sample through, for example, or that gas phase sample, and then selectively trap the compounds of interest. We could also be using things like solid phase microextraction, stir-bar sorptive extraction, and high sorb, etc. And again, to be very selective in what we're going and trapping. Quite often the case is, though, you can't be selective enough. So we go to the next step in our process. Think about then our sample preparation. This is usually done back in the laboratory. So we've taken our sample back from wherever the location was. And the aims of sample preparation, this is not an exhaustive list, by the way, is to concentrate our analytes. So for example, again, if we go back to our water sample, for example, we could be going and having to analyze to get down to the limits of detection. We need a litre of water. Now, we can't go and inject a litre of water into our GC. So therefore, we need a concentration technique to then reduce the volume of that down, and also maybe put it into a solvent which is more GC amenable. We could be, in the process, removing matrix. So we've got high loading of matrix, non-organic material in there, we could be needing to remove all of that. So again, we want to selectively remove the matrix and make sure we don't lose any of the target compounds. And that is one of the problems with our sample preparation is, could we lose some of those compounds? Potential loss of analytes, and the concentration of the matrix too. So if it's not selective in our sample preparation, and we're going down from 1 litre down to, say, for example, 1 mil, then we're going to get a big concentration in the matrix as well, which of course then could dirty the rest of our instrument. So different techniques that we could be using here, which are again selective, things like solid phase extraction, where we selected the solid phase to selectively either extract the target compounds and allow the matrix to move through, or vice versa, where we're then trapping the matrix and then allowing the analytes to pass through, depending again on the types of compounds in the matrix that we're actually looking at. We could be using liquid extraction, where again we're selecting the solvents to selectively extract the target compounds and hopefully leave behind that matrix. We could be selecting something like headspace analysis, where we're looking at volatile compounds, and therefore then we're doing matrix modification and helping those analytes of interest to move into the headspace and leave the higher molecular weight matrix compounds in our sample. So then we are then selectively removing that headspace in the compounds of interest. And again, the same thing with purge and trap, but however with purge and trap, we are then passing those volatiles through a sorbent trap, and again, that could then be selective to only trap and concentrate our target compounds and, for example, ignore water, as we talked about with the example just now. So we've got lots of different ways of thinking about it in our sample preparation stage. One of the main things is we don't want to lose our analytes at the expense of ignoring the matrix and not selectively extracting the matrix as well. So we've got to make sure then that we keep and try and maintain all of our analytes to get through of that process. Later on, we can look at then selecting and being selective for our target compounds over a matrix in a future step, as we'll go through. The next step is our sample introduction. Now, in my experience, this is something that is overlooked a lot, okay? So, when we are introducing our sample onto the head of the analytical column, we want the aims of that are to be repeatable and reproducible, to transfer a representative portion of our sample onto that GC column for analysis, and the most important thing is to be in a narrow sample band, meaning that all of the molecules of the same compound go onto the column very close together to obtain sharp peaks. And of course, we don't want any chemical change when we do this. So we don't want thermal degradation, we don't want reactions to occur, we don't want activity in our inlet when we go and transfer that through. So again, we've got lots of GC inlet liners that we can select for activity that are well deactivated. But in our inlet, this is a mode of being selective. Now, we can, when we transfer our analytes from the inlet onto the column, we can carefully control the temperature. This means that all of the target compounds that we're interested in transfer onto the GC column, and we keep as far as possible, the involatile material in our inlet liner. Now, if you were doing 1D GC, it's quite normal these days to do back flushing of our GC column. So therefore, if we do transfer any high molecular weight molecules onto the column, rather than purge them all the way through our GC column, we're back flushing it to get them back out through our split exit in our inlet. However, we don't tend to see this in GC times GC because we've already got quite a complicated setup. So when we go into GC times GC, what we want to make sure is that everything we transfer onto the column can go through the column and through the system, and we can remove it so we don't have carryover to the subsequent runs. We also don't want dirty, high molecular weight material damaging the front end of our column, because if we have to trim the column, what's going to happen to our retention times? They're going to shift. So carefully controlling the inlet temperature is really important. We could be wanting to get more sensitivity by doing a large volume injection. This is a selective technique as well, because in the inlet, what we're doing is vaporizing the solvent, concentrating our sample in the inlet, and then we're doing a splitless transfer to the GC column. So we are selectively removing that solvent, like a volatility cut. Now, selective discrimination also can be used further than that, because what we can do is very selectively take our volatility cuts from our inlet and transfer only of those to our GC column. So already in this example here, the controlled temperature is removing the back end of our sample, the higher molecular weight cut. Large volume injection is removing the solvent, which is very volatile. So we can then extend that further. Now, one of the biggest problems I see with inlets is that the temperature of the inlet is so high that we're transferring compounds that can't sometimes come off the GC column at the maximum column temperatures. Generally, what we're looking at is an inlet temperature which is well below the boiling point of our sample, of our analytes. If we have a puddle of water outside, boiling point of water is, who's falling asleep? Who shall I pick on? Boiling point of water is 100 degrees C. Does it need to get to 100 degrees C outside for it to evaporate? No. What's the minimum temperature for a puddle of water to evaporate? 5, 7 degrees C? It will start evaporating, won't it? Well below the boiling point of the solvent. What assists it? Things like pressure. The higher the pressure, of course, the boiling point will increase. The lower pressure, it will have a slightly lower boiling point and become more volatile. What else? The wind. Yeah? On a windy day, it evaporates really quickly. So we can translate that into our GC inlet liner. So the wind is the flow through the liner. If we have a split injection, everything will evaporate much faster, and we'll probably get higher boiling point compounds onto our column. With splitless, it's a slower transfer process. So many years ago, when I did my master's, I investigated this, and apologies to those like I know Jacques, who I've heard this presentation before. But what we looked at is basically the effective temperature of when our compounds came out of the inlet liner. Now, as we can see just here, let's get a little spot. This is the injector temperature that has been set, and that's a fixed temperature. And then we've got basically the 100% of the area where everything was transferred. So this is when those compounds, these hydrocarbons, ranging from C14 to C36, were injected, so everything was transferred to the column. Then we look at the proportion that's transferred at different temperatures. So if you look, for example, here at C36, we can see at 220 degrees, basically nothing is transferred onto our column, or all stays in the inlet liner. If we increase that now to about 280, 290 degrees, we're getting the majority of that compound transferred to our column. So essentially, and it's a very, very sharp cutoff, as we can see just here. So therefore, we can go, by changing the temperature by 40, 50 degrees, we can go from none of it transferred to all of it transferred. So we can use this then to actually identify if we wanted all of these compounds here transferred onto the column, because that's what we're interested in, then we'd know that we'd need at least 180 degrees C to get C24 transferred across. But at that temperature there, none of the higher boilers will transfer across, and they will stay in the inlet liner. So this is what we want to be using then to be selective of transferring our analytes onto our column. is a chromatogram of an N-alkane wax. Lots of different hydrocarbons up to about C70 and that. Now, if we wanted to look at and analyze all of those compounds in there, you just set your inlet temperature to a high temperature and transfer everything onto the column to get that separation. But what happens if you only want interested in a proportion of those, a volatility cut? We can then go and, on the inlet, control the temperatures, control the flows, and take these different cuts from there. So at the top we've got here is our chromatogram where everything is transferred. Here, on the second one, is where we get 100% of C20, and everything before that is transferred onto the column, but we're not interested in the back end. Now we see a small amount here, and that is due to the split. Okay, so I'll show you in a minute. Actually, it's going up to the final temperature to still go and clean the liner out afterwards. And the amount that's transferred of these depends on the split ratio. But of course, you don't have to heat the inlet higher than what you need to transfer 100% of the C20. And of course, what you get is, because it's not a straight off temperature cut, you'll get a little bit of the C22 and a little bit less of the C24 and so on and so forth as we go through. Down here at the bottom, what we want is to transfer everything C40 and beyond, all of that to the column, but as little as possible in the front end. So again, what we've got here is we're purging this with a split, so we still get a small amount transferred to the column, but the majority of the front end there is gone, and 100% is C40, and everything beyond that is now transferred to the column. Most difficult bit is the middle bit, and this is where we've got C30. C30 is the only thing we're interested in. We've purged everything in the front end, and we've purged everything in the back end. How do we do that? We use a programmable temperature vaporizer, and we control our temperatures and our flows. So if we are selecting only that C30 and nothing else, then what we start off is we inject with the inlet temperature cool and the split exit open. We then ramp it up to a certain temperature to get everything before C30 purged out the system. Or again, it is a split, so you still get a small amount onto the front end of your column. You now get to the point of where you want to transfer your C30. So we go across into splitless mode, and then we ramp to another temperature. Now this is hot enough to transfer the C30, but as little beyond C30 as possible. After we've transferred the C30 onto our column, what we do again is open up our split exit, and again, ramp the temperature further to then go and clean our inlet liner. And therefore, then, we can be very selective in what we are transferring. Now, you might not be interested in any of this, but one of the important things is, if you get your inlet temperature wrong, you can lose a lot of information. Also, if the inlet temperature is too hot, you'll put a lot of higher boilers onto the column, which you might not be able to get off. So we really need to be thinking about selectivity on our inlet. Next step in the process is our analyte separation. So here what the aim is to separate the analytes of interest from each other, as well as any co-extracted matrix components. So the problems are there enough theoretical plates for the large number of analytes and matrix peaks? We could get mixed characteristics, so therefore a selection of the phase is good for some classes of compounds and not others. So there's different techniques, some of them we talked about over the last 2 days. So first of all, just for a simple 1D system, we're thinking about selecting the best column stationary phase by thinking about like separates like. So therefore, you're selecting one that matches, for example, the polarity of the compounds of that you want to go and analyze. Heart cutting is where we can take a small portion that's not separated on one column and transfer it to a second column, which is great if you've got a few peaks that are co-eluted that can't be separated. But of course, then we go into our comprehensive GC times GC. So I'm not going to go into detail here because we've been talking about it yesterday and today. But that's now where we are choosing 2 different column stationary phases. And we're then getting our selectivity based on both of those. And of course, we could be pulling in a different technique altogether, like liquid chromatography, as was discussed yesterday. And we are then coupling LC and GC to get 2 different selectivities, 2 different ways of getting our separation. So that's about analyte separation. And of course, then you can produce, if you're going to the GC times GC, this is the most powerful that we've got of our separation techniques, where we can then go and select select, for example, very simple diesel analysis, and so we can then select our alkanes and our aromatic compounds, etc. Again, I'm not going to go into detail here because we've been talking about it a lot yesterday and today. So that leads me on to Analyte Detection. So again, another place where we can think about using selectivity for the analysis of our samples. So the aims here are to have the adequate sensitivity for all of the target compounds that we're interested in, thinking about all of our concentration effects, etc., in the steps leading up to this, like, for example, our sample preparation, or if we're doing large volume injection. What we want ideally is to have a linear response over the concentration range that we're interested in. We want it to be stable, reproducible, and give us the required information for confirmation of the presence or absence of our compounds, or give us the ability to identify our compounds of interest. And of course, when we're thinking about a detector selectivity, if we're selecting the most suitable detector, it could improve the sensitivity, so we could get better method detection limits. It enables us to observe our target compounds and ignore, physically not see our matrix peaks. Okay? So therefore, it is only going to produce a response to our target compounds. And therefore, we're reducing our matrix interferences. And of course, also, it gives us easier quantitation. Because if you are only seeing a peak and it's got baseline to baseline resolution, we can integrate it much easier and more accurately as well. So when we're thinking about our detectors, we could be using it as a universal detector, because if you want to see everything, you need a detector that will see everything. So it goes back to the original question for our sample. So we can see most organic compounds, for example, like an FID, a TCD, an HID, or a mass spec, where we're acquiring the full scan range. Oh, this is our Pegasus BT 4D system, which has just been installed in our lab last week. And then we could think about selective detectors. For example, the micro-ECD responds to only compounds which are capable of capturing an electron. We can have SCDs, sulfur chemiluminescence detectors, nitrogen chemiluminescence detectors, etc., which are responding to certain atoms. And of course, if we're using a mass spectrometer on the end of our GC, then we could be using things like negative chemical ionization to get more selectivity, using selected ion monitoring, using MSMS, where we're producing our secondary ion chromatograms, and using high-resolution mass spectrometry, where we can get multiple decimal places, which again means that we don't see those co-eluting matrix interferences. So we've got a range of different ways, but each of these individually is only one way of doing it. We have the most powerful method when we combine all these different methods of selectivity. Finally, data analysis. So here we want to be confirming the presence or absence of our compounds, and we might be wanting to identify unknown compounds. So problems could be that our analytes and our matrix are still co-eluting. So again, some of the presentations we've seen over the last 2 days mentioned that even with GC times GC, they still might be getting some co-elutions. So having the mass spectrometer then, again, adds us an extra dimension of data and an extra way of being selective. So with this, we could be selecting, for example, for quantitation, a mass which is a unique mass, i.e. it's not present in co-eluting compounds. Okay, and it's quite good and big in our mass spectrum as well. And we could be using our deconvolution as well. So therefore, that's a way of pulling apart our mass spectra and having a look to see if we have co-eluting peaks, if they have differences in the ions in the mass spectra that we've got in there. So for example, here we've got 3 peaks which are co-eluting, and if you moved across that peak, you would see the change in the mass spectra. So that's great to see it, but you need a program like deconvolution to then enable to unknit it all and pull apart and pull out cleaned up mass spectra for each of those individual components, which could be a mixture of a matrix peak, an interference, and your target compound, which are all co-eluting together. And of course, if you did a library search of a mixed mass spectrum, it's not going to give you a good match. So if we are then combining our GC times GC with, for example, a time-of-flight mass spectrometer, that enables us to then go and do our deconvolution as well. So just to kind of summarize then, what we want to do when we're thinking about analysis is to break it down into individual steps. What is happening from our sample collection all the way through to our data analysis. how are we going to then use selectivity in each of those steps? So in our sampling, selectively extracting our compounds of interest in situ from wherever that location is. In our sample preparation, when we're selectively extracting the target compounds, leaving behind the matrix. In our sample introduction, where we can do a volatility cut of our analytes of interest or compounds of interest onto our GC column. And even if we want to look at everything in the sample, we should not be transferring those high molecular weight compounds which you can't get off the column. Analyte separation, so selecting our stationary phases, whether that's 2 dimensions or 1 dimension. Of course, again, GC times GC being the most powerful. Our analyte detection, only seeing the compounds of interest, being very selective. And, of course, things like data analysis, where we can select unique masses and use things like deconvolution. So this is what we should all be doing with our methods, is having a critical look at them from start to finish, how we can introduce more selectivity, not just to the separation, not just to the detection, but to the whole of the sample analysis. So I just want to thank you all for listening. I also want to thank Alan and Nick from LECO for inviting me to present here today, my colleagues at the Open University, where I have a lab and we do lots of analysis, the Royal Society of Chemistry, of course, and just being launched in November, it's being published, is a book on how do you do things in GCMS. So it's not a theoretical book, it is a book which is actually we've written, because I'm very much involved with the Pan-African Chemistry Network in training 400 analytical scientists across Africa, and we've written this book to go alongside that, and then lots of people have said, actually, that would be really useful for us as well. So it takes you step by step from sampling through to data analysis and how to optimize your parameters and what the parameters really mean. So thank you for listening.